so if you look at some projects, find 3 or 4, 2 or 3 that seem like they're interesting to you. Then come back and talk to me, and I can point you in the right direction, a direction where hopefully you can get something interesting done. At least that's my hope. Okay, any questions about the project or anything like that, what's required or what's going on? Again, I'd like to get proposals in about 2 weeks or so. So it's, try to find me and let's start talking. Any other questions? Okay. The other question might be about the midterms. Again, the midterms have sort of been graded. I don't want to give them back yet because they're still, I want to double check things a little bit more. But basically they looked pretty good in general. Not always, but not all of them, but looked in general pretty good. Okay, and we'll fill in the details later. Any other questions? Okay, good. Okay, so what have we been talking about? This is, I guess, lecture 12 of CSE 547. Last class, we started talking about a couple of counting problems, okay? And the idea was that, again, there's lots of different sort of discrete structures that occur over and over and over again, okay? And that learning to see the world in this, in terms of these structures, okay, is a useful thing, because you can sort of say, oh, this is, this has to do with cycle structures, okay, of permutations. That's what we talked about last class a little bit. This has to do with a set partition. Okay, it gives you a language to talk about things. We've also seen examples where of sort of counting problems, the idea of breaking things into recurrences and counting them. And I'd like to continue in that vein today by looking at a couple of other sequences that are defined by recurrences. One of the students in the class just brought me a book, which I just want to show you just because it sort of shows the same thing we ended up yesterday with in a different guise. There's a book on discrete mathematics, and it's talking about a trick with sort of shuffling cards, okay, a different kind of card trick. It can also be viewed in terms of cycle structures of permutations. So suppose, let's say that you had 12 cards, okay, and you have the cards are ordered in your deck, okay. You then go and these are numbered 1, 2, 3, 4, 5, 6, 7, 8, 9, 12. Suppose that instead of you take those cards, you pick them up, and now instead of shuffling, putting them down, let's say row by row, you put them down column by column. So you take a current deck, okay, and if you listed them, if you put them out by if you put them out by rows, okay, that somehow if you take the deck, okay, and given the deck, I believe it is that you put them out like by rows. Okay, that you do an operation, a shuffle-like operation, where you take the cards as numbered out by rows and rearrange them so they're numbered out by columns. Okay, and this can be done by not card shuffling using perfect shuffles the way we did, but simply by putting them out in a column major format instead of a row major format. Okay, you can think of each one of these the operations of going from a deck that looks like this to a deck that looks like that. Okay, so basically again, here you have a situation where you have 12 cards. They're picked up in row major order. So you pick them up like this, and then you redeal them in a column major order. Okay, that's an operation on the cards. Okay, how many times could you do that? Just pick up the cards, okay, by rows, put them out by columns, pick them up again. How many times would you have to repeat that till you got to the original deck? I've seen this card trick. I've seen this trick played on me when I was a kid. Okay, I don't know if any of you have seen such a trick. But what does it work? Well, what they show you is they find the cycle structure of the permutation. Here we map 1 to 1, 2 gets mapped to 5, 5 gets mapped to 6, 6 gets mapped to 10, okay, 10 gets mapped to 4, okay, and 4 gets mapped to 2, okay, which is the exact start that we had of that cycle, okay. So here you have the cycle structure of permutation that you get by if you deal cards out in row major order and pick them up in column major order. This is what you end up getting for the permutation. And again, that shows that if you cycle this thing, okay, by using the same kind of arguments we used before, that if every time I did a one of these operations, each card shifts one position in the cycle, this argues that after 5 shuffles, okay, 5 put 'em downs and fix 'em ups, you get back to the original state. Any questions about that? Okay, I'm not trying to teach you too many card tricks, but just to sort of let you know that whenever you're dealing with an operation, mapping things to other things, a bijection, implicit in that is a permutation. Okay, and thinking about the cycle structure of that permutation can pay some dividends. Okay, and thinking about how you analyze it. Any other questions? Okay, thanks. So here, remember to pick that up. Okay, what I want to do is to talk about first another problem on permutations. Okay, and another sort of thing, sort of property of permutations that turns out to lead itself to another recurrence for practice. Okay, and lets us, talk about some other things. And it has to do with how many permutations of n things are there with k ascents, okay, or increasing neighbors. Okay, so let's think about what we mean by that, okay? We say that if we have a permutation, it's an arrangement of things. There's n factorial different permutations that we all agree on, okay? A given permutation has a certain number of ascents, okay? Namely, here is not an ascent, it's a descent, okay? Here is an ascent, because 1 is big, 2 is bigger than 1. 2 to 3 is an ascent, okay? Any questions about that? What we mean by an ascent? Okay, in a permutation, if you want to think of it, a ascent is when we have a pair of adjacent numbers that increase, okay? What's the maximum number of ascents we can have in a permutation of n things? N minus 1, right? Because it's got to be between pairs. What's the fewest number of ascents you can have in a permutation? 0. How do you get 0? Okay, if they were all in reverse order, right? If the permutation was in reverse order, you've got 0 ascents. Okay? In general, we can now talk about how many, we'll call this thing something called the 4 bracket 2, as counting the number of permutations of 4, consisting of 2 ascents. Okay? My claim is that there are 11 of them. Let's think about that. How come 11? Well, if we've got 2 ascents, let's see if how we can break this thing down. It seems to me that the 2 cases are, I think how we can, okay, here I have what I think are the 11 ascents. Let's think how we can break that down, okay, into, sort of into counting these. This may seem to be a little trickier here. We can think of all the permutations where the ascents are between the first and last pairs. Let's sit down and think about that, okay? If we're going to have 2 ascents, okay, my first claim is that the first number, okay, cannot be a 4. Okay, if it's going to be an ascent after the first one, our choices are that we can have a 1 and a 3, okay, a 1 and a 4. These are the only possible ascents you can have for the first choices, correct? Every ascent is going to have to be, you have n minus 1 choices for the first one, okay? And then the remaining number of elements bigger than that, choices for the second spot, okay? So I think that it should be clear that these are all the possible choices for the first one. Once we have the first 2 elements in our ascents fixed, if we want to guarantee that from here to here there is an ascent, there's only one way to order them, correct? So once you fix the first ascent, the choice of elements for the second ascent is sort of given, okay? Any questions? And we know that you can't have a 1, 2 as the first lead here, because if you have a 1, 2 here, you're guaranteed that there's going to be an ascent in between there, okay? Any questions about that? My claim is, maybe we look at this thing, it's maybe not quite so obvious. I think that by an exhaustive search, you could look through all 24 permutations There, in fact, these are the only 11 with 2 ascents. Any questions? So how do we analyze, again, count these things? Okay, our goal should be, in general, whenever you're given accounting a problem, you think about recurrences and you think about special cases. How many permutations are there? Okay, suppose k equals 0. How many permutations are there with 0 ascents? Well, that we agreed there was only one of them, correct? How many permutations are there with 1 ascent? Well, that may not be quite so obvious. How many permutations are there with n minus 1 ascents? That we agreed meant that since there were only n minus 1 pairs, there was only one, the total order. Okay, that was good. What other special cases can we think about here? Okay. I claim that there's a certain symmetry, okay, about, just like there was, remember, binomial coefficients, there was a symmetry that n choose k was equal to n choose n minus k. Why was that? It was because, remember, picking a subset of k things, okay, forced was the same as not picking a subset of n minus k things, right? A similar property will happen when we talk about a sort of ascents in a permutation. My claim is that if you have a permutation of n things, okay, it's going to have, if it has k ascents, that means that it's going to have n minus k minus 1 descents, right? There's only n minus 1 things, pairs. Each one is an ascent or a descent. If we subtract the ascents, we get the descents, correct? Now, what happens if we take each permutation and reverse it? Okay? This is kind of an interesting way of counting it. If we take all permutations, okay, that have k ascents and reverse them, what do we get? We get all permutations which have n minus k minus 1 ascents, right? Because taking a permutation and reversing it turns an ascent into a descent, correct? How many people see this? Okay? So what's interesting is you've got a, sort of, again, a similar kind of identity as before. Okay? Any questions? So these are sort of special cases. What is the general case, okay, of trying to come up with how many permutations there are with exactly n ascents, okay, with exactly k of ascents, okay? This general strategy we should be looking at is the same as we've seen before. We're going to want to take the last element and stick it someplace, okay? Where can you think of sticking it, okay? Well, if we stick it, the nth element between two elements, that, I mean, if you think about what we're going to be doing, I'm going to be given a permutation of n minus 1 elements. I'm going to insert it into a permutation, the nth element into that permutation of n minus 1 elements. When I insert it, it's either going to split an ascent, meaning it's between two elements that are increasing, or it's going to be, or it's going to go at the beginning of an ascent. Okay? The other possibility is that I could insert it, okay, in the middle of a descent, okay, or insert the element last. Okay? So if I insert a new element into a permutation, okay, either it's going to split an ascent or a descent, or it's going to be at the beginning of something, the permutation, or it's going to be at the end. Okay? My claim is that whenever I split an ascent, okay, that means that the total number of ascents is going to be unchanged. Let's think about that. Does everybody agree that here I have one ascent? If I insert another element in, there's still one ascent and one descent. Okay? If I insert another element in the middle of a descent, I've created one. Okay, I have if I insert it in the middle of a descent, okay, I will increase the number of ascents, right? So this is an increase. This is the same. This, I claim, is going to leave it unchanged. This, I claim, is going to increase the number of ascents. Correct? Those are really the only 4 possible cases. So what do we want to do? Okay. If we increase the number of ascents, okay, that means that we want to consider, if we're going to create a permutation of n things with k ascents, okay, either we're going to be starting from a permutation of n minus 1 things with k minus 1 things, ascents, okay, or we're going to start with a permutation of n minus 1 of n minus 1 things with k ascents, okay. So it should be clear the recurrence looks something like this plus this with the appropriate weights. How many spots are there to insert things, okay, so that we don't do it, okay? In the first case, every ascent, okay, if we're going to be, here we are, okay, let's just stop to think about where these things come from, okay? Here, okay, actually, sorry about that. Here we've got, we're going to be increasing the number of ascents, okay? So we're going to be looking at the bottom 2, okay? How many ways are there that we can insert something to increase the number of ascents? Well, every time there was a descent, okay, that corresponded to a place we could have inserted it to add 1. There were n minus k minus 1 descents, plus there was 1 at the end, the last thing, okay? So that's where we get n minus k, okay? Because this is n minus k minus 1 plus 1, okay, is how many places there are to insert it so that we add a ascent. How many places were there that we leave it so that we don't add an ascent? Well, that corresponded to these 2 cases. We could have put our number, the biggest number first. There was 1 possibility there. Or we could split one of our existing k ascents, okay? And that's where the k plus 1 comes in, okay? My claim is the number of permutations of n things with k ascents is k plus 1 times the number of permutations of n minus 1 things with k ascents plus n minus k times n minus 1 sort of permutations with k minus 1 ascents. Any questions about how many people sort of see the recurrence and believe it? How many people don't see it and would like to see it again? Or any questions about that? Okay. How do we do it? Well, let's take a look at this thing. The way to look back is to take one of these things and look backwards. Let's say that here I've got a permutation. Let's put 6, 5. Okay, let's just take that as being a permutation. How many ascents are there here? Okay, well, if we look at this thing, there is 1, 2, 3 ascents. Okay, this is n elements, n equals 6, k equals 3. If we delete this thing, what did we get? We had a permutation 1, 3, 4, 2, 5. How many ascents did we have? Okay, 1, 2, 3. Okay, we did not change the number of ascents when we added that. Why was that? Because it split it split an ascent and left that unchanged. Okay, so really what we need to do is to count how many ways could we insert that last element without adding it, while adding an ascent. How many ways could we insert it without adding an ascent? To not add 1 involved splitting an existing 1 or sticking it at the very beginning. To add 1 involved splitting something that wasn't an ascent, which is everything that wasn't one of those k, n minus k minus 1, or the special case of the last one in the permutation. Any questions? Okay. I urge you to go through and validate these things, think about them, okay, and make sure you understand what the recurrence basically is doing. Okay. Any questions? Okay. The act of being able to generate a recurrence is sort of really the essence of counting. Okay. These particular numbers occur often enough that, again, they're given a name. They're called Eulerian numbers. Okay. Can anybody think of a reason why you might care about the number of ascents in a permutation? Where, let's say, in something in computer science where the idea of thinking about how many ascents there might be could factor in? Okay, in sorting. Okay? The number of ascents is some kind of a measure of how sorted something is. Okay? If you have a permutation that's completely sorted, okay, it's got a lot of ascents. If it's completely scrambled, okay, it should have fewer ascents. How many ascents would you say a permutation, a random permutation of length n, has? Okay, let's stop and think about it. A rough idea. How many ascents does a permutation of n things have if it's random? Okay. N by 2. Why n by 2? An analogous argument, the way that I would think about it, is to think that if you think about it, if you take a permutation and reverse it, every ascent became a descent. There's no reason why it's going to have more ascents than descents, if you want to think of it that way. Because every permutation somehow appears, both the permutation and its reverse, okay, will both appear in the set. So if you count how many ascents, if you take the n over, here's probably the easiest analogy. If you take a look at it this way, there are a total of n minus 1 ascents or candidates in a permutation, right? There are n factorial possible permutations, okay? If we take every permutation, we could take the permutations and partition them into n factorial over 2 permutations and its reverses. Okay, so every permutation has its reverse. Okay, we could pair up each permutation with its reverse and come up with now n factorial over 2 pairs of permutations, p plus p and p reversed. Okay? If we take each permutation and its reverse, together they're going to account for n minus 1 ascents, if you take each permutation and its reverse. Correct? So the total number of ascents in all permutations is going to be n over 2 factorial times n minus 1. Okay? Everybody sort of see? So if you want to figure out what it is on average, you divide that by n factorial, and you get n minus 1 over 2, okay, is the average number of ascents in a random permutation. Any questions? Okay? Again, these things come up in, you know, thinking about sorting and other sort of things having to do with permutations. Any questions? Okay? But even if you're not interested in that, it should still be just a case of another counting sequence, okay, that sort of increases your repertoire of such things. Any questions? Okay. What I'd like to now talk about, probably for the rest of the class, is the, if you want to think of it, the mother of all recurrences that count things. Okay? And these are the Fibonacci numbers. Okay? You may want to skip ahead a little bit. Okay? What are the Fibonacci numbers? Okay? The Fibonacci numbers, how many people here have never heard of the Fibonacci numbers? A couple of people, okay? Most people have probably seen them somewhere along the line because they're a very, very cute sort of number sequence that comes up in a lot of interesting applications, okay? The reason somehow Fibonacci numbers come up a lot, okay, if you want to think as a meta reason, is because they're going to be defined by the simplest recurrence relation, that's the simplest interesting recurrence relation known to man. Okay? F sub n equals F sub n minus 1 plus F sub n minus 2. Okay? If you think about it, a recurrence relation of the form F sub n equals F sub n minus 1 plus something that's not recursive, that's a simple summation. We saw that earlier on in the semester. This is the simplest recurrence relation you can have with 2 terms in it. And it's sort of a mathematical truism that if you've got a very simple structure, it probably comes up. There's reasons why it comes up. Okay? And if you take this recurrence relation and couple it with the initialization conditions, f sub 0, okay, equals 0, and f sub 1 equals 1, that defines the Fibonacci numbers. We know that if 0 is 1, the nth Fibonacci number is the sum of the two previous Fibonacci numbers. 0 and 1, the sum of them is 1. 1 plus 1, the sum is 2. Okay? 1 plus 2, the sum is 3. 2 plus 5, 3 is 5. 3 plus 5 is 8, 13, 21, 34, 55. Okay? Any questions about where the Fibonacci numbers come from? They come from this particular sequence. Okay? Now, why are they called the Fibonacci numbers? Well, there was a mathematician named Fibonacci who was thinking about them. Why was he thinking about them? It was about 1200 AD, so he thought about it a long time ago. Okay? He was actually trying to count how many rabbits you would have after you start with a breeding pair of rabbits. Okay? Close the door and let them breed. Let's say that they could breed every year. Let's say every year you had a situation where a rabbit couldn't breed the first year, but could breed the year after. Something like that defines a model like this, a recursive model like this. And so that's why people started thinking about Fibonacci numbers. There's no evidence rabbits breed that way. Okay? But on the other hand, there's lots of other things in nature that do seem to observe the Fibonacci numbers. Okay? One of the ones that you hear most often has to do with the number of leaves somehow on petals on flowers. Okay? Now, in fact, I'll show you an example. It's a little bit murky how it comes up exactly. But you could say that in certain flowers, the number of leaves, number of petals you get tend to be counted by the number of Fibonacci numbers. Okay? So if you believe that, actually, how many of you are familiar with the game She Loves Me Not? Okay, you take a flower and you peel things off. You say, she loves me not, she loves me. And depending on what the last petal is, either she loves you or she doesn't. Okay? That said, is there an optimal strategy to do it? Should you start out saying she loves me or she loves me not? Okay? I think if you believe Fibonacci numbers are, are the number of leaves are counted by Fibonacci numbers, should you count randomly, or is there an advantageous strategy to starting either on she loves me or she loves me not? Think about it. Okay? Why would one be a better strategy than the other? Okay? If you think about the question of whether she loves you or loves you not is a question of the number of leaves mod 2. Correct? Because there's only two things. You start from one and it's oscillating, loves me not. Okay? So the issue is then whether or not you have an odd number of leaves or an even number of leaves. Correct? If you look at the Fibonacci numbers, you'll notice that one out of every three Fibonacci numbers is even. Okay? And then it's even, odd, odd, even, odd, odd, even. So that should give you some hint as to where to start. Okay? Any questions about that? Okay? The way you always hear it cited that Fibonacci numbers are related to flowers. And it's usually a little bit murky, I'll confess, where they come in. But one area where it comes in is in sunflowers. Okay, if you look at sunflowers and the arrangement of sort of the seeds in sunflowers, they're apparently arranged in these sort of interleaving spirals. Okay, I think I believe that from the way I remember sunflowers looking. Okay, and it turns out that, again, the number of spirals you get alternating each way, okay, turn out to be Fibonacci numbers just based on how they grow. Any questions? Okay, that should not be convincing, but it's just take it as a statement, and you may believe. Okay, again, there's a lot of interesting things about Fibonacci numbers. In fact, one of the things that's nice about them is that there's just a tremendous number of interesting identities associated with them. In fact, there's a journal called the Fibonacci Quarterly that is published solely to report the latest news about Fibonacci numbers. There's that much interesting things with Fibonacci numbers. Any questions? They're all over the place. So where do they look? Where are they? Well, one place you can find them, if you look carefully, okay, is in Pascal's triangle. Remember what Pascal's triangle were? That was what somehow was a presentation of all the binomial coefficients. Remember that we had each, as n increased, 1, 2, 3, 4, we had n elements on the nth row, each one corresponding, this is n choose 0, n choose 1, n choose 2, and so on. What's interesting is if you take the Pascal's triangle, and instead of thinking about rows, think about diagonals, okay, sort of at a slope of half that, okay, you'll see here that the first diagonal contains the top one. The second diagonal contains the one on the right, second row's one on the right. Third diagonal consists of the first one from the second row with the last one from there. Next one consists of the center element and the right. Next one contains those three. So the number of elements is 1, 1, 2, 2, 1, 1. I mean, the number of elements on each diagonal is 1, 1, 2, 2, 3, 3, 4, 4, and so on. If you look at it, the sum of the elements on each diagonal, okay, is in fact going to be a Fibonacci number, okay, which is kind of a weird thing to be, okay. And, you know, so basically, why does this happen? The major reason is simply that it was saying that by definition, the sum of two successive diagonals equals the third. Because of that is where you get the Fibonacci numbers from. It's that same kind of a recurrence that we have there. Any questions? Okay, I'm not going to prove that, but you can see that. Any questions? Okay. What's interesting about the Fibonacci number, again, is that there's lots of identities, and these identities are fairly easy to prove by using some of the tricks we used about summations. Okay? So by perturbation, what we meant with sums was this idea that we would take a sum, name its quantity, and then add something to it, okay, and see how it changed. That was sort of what I meant by perturbation. Induction, we saw that was an idea that once you had an answer, okay, you could prove it correct, okay? Let's now prove that the sum of the first n Fibonacci numbers is the n plus second Fibonacci number minus 1, okay? So sums of Fibonacci numbers can go away and be reduced by one Fibonacci number on its own, okay? How can that be? Well, let's take a look at it. First, we can say, let's define that S sub n is the sum of the first n Fibonacci numbers, okay? By definition, f sub n plus s sub n minus 1 is s sub n, right? Okay, which is the sum of the first n Fibonacci numbers, okay? The Fibonacci numbers have this wonderful recursive definition. So we know that f sub I is going to be equal to f sub I minus 1 plus f sub I minus 2, right? Okay? That means we can now partition our sum into two subsums, okay? The sum as I goes from 1 to n of f sub I minus 1. What's that? That's the sum of, okay, since if you think about it, we have to change, you know, it's not quite the same sum, okay? But this is summing up the Fibonacci numbers from fib of 0 to fib of n minus 1, right? Here we have s sub n is equal to the sum of the first Fibonacci number to the nth. My claim is we can write that as s sub n minus 1 plus fib sub 0, okay? How many people are with me so far? Okay, that should be pretty easy. Now, fib sub 0 is 0, right? We start counting the Fibonacci numbers from 0, 1, 2. Let's look at the other summation. That's a little more interesting. Here we have the sum of f sub I goes from 1 to n, of f sub I minus 2. That means we're summing up f sub I minus 2, f sub n minus 1, dot, 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 f sub 0, f sub I minus 1, correct? If you look at this thing, the endpoints here include f sub 0 and f sub 1 minus 1. it's clear we can write the sum from 1 to n minus 2 as s sub n minus 2. We can write f sub 0 as 0. What is f of minus 1, the minus first Fibonacci number? This may look disconcerting. Okay? My claim is that it sort of is defined by our recurrence. We've said that for all Fibonacci numbers, the nth Fibonacci number is the sum of the n minus first and the n minus second, right? So if we know what f sub 0 is, and we know what f sub 1 is, my claim is that f sub 1 is going to have to be f sub minus 1 plus f sub 0, which means that we could solve for f sub minus 1. Okay? Any questions about what I'm doing here? If you believe the definition, this then defines the negative number obviously. Okay? If that's true, f sub 1 is 1, f sub 0 is 0, f sub minus 1 is 0. Okay? Any questions? That said, what do we now say? We now say that f sub n, okay, is equal plus s sub n minus 1 is equal to s sub n minus 1, those things cancel, plus s sub n minus 2 plus 1. By rearranging the terms and changing the variables, okay, so that instead of thinking of it in terms of, instead of just thinking, that says that s sub n minus 2 is equal to f sub n minus 1. By changing the variables labels, we get this. Any questions about that? Should be straightforward. Now, it should be straightforward, but you might be feeling queasy about this. Okay, that's a reasonable thing to feel queasy about. What do you do with a Fibonacci sum or with an expression when you feel queasy about how you derived it? You double check it. Right way to check it is a proof by induction. Okay? So how would we prove that by induction? Well, we know that s sub n minus 1 plus 1 is, if we assume that this is true inductively, up to n. We know s sub n plus 1. Well, without any assumption, we know that that's going to be equal to f sub n plus 1 plus s sub n. The sum of the n plus first Fibonacci numbers is, just take off the largest one. This we know has to be equal to that. We also know that f sub n plus 1 plus f sub n plus 2, this is by definition equal to f sub n plus 3. And so again, it's very, very simple inductive proof once you have the sum. Okay? Any questions? These inductive, the fact that you can take pairs of Fibonacci numbers and just erase them with another one is what makes it a joy to work with these guys. Any questions? Okay, good. Let's look at one other curious identity, okay, on Fibonacci numbers. Okay, something called Cassini's identity, okay, which states that f sub n plus 1, the nth plus first Fibonacci number, times the n minus first Fibonacci number, minus f sub n squared, is plus or minus 1, depending upon the parity of n. Okay? Any questions about what that means? It says basically the Fibonacci, that the Fibonacci number, the product of the Fibonacci numbers above and below, okay, it, are almost exactly what you call it, the nth Fibonacci squared. Okay? Any questions? How would you prove such a thing? Okay? The right way to do it is you would do an inductive proof. Okay? We'll assume that this thing holds for a while. Okay, that's the easiest way to do it. What do we now know? F sub n, we know that, let's think how we can sort of play with it. There's probably lots of different ways you can play with this. Here we could get rid of the f sub n minus 1. If you think about it, here you've got f sub n plus 1. Here you've got f sub n. If we want to mash on the identity, let's get rid of the lower ranked terms. Okay, how can we get rid of the f sub n minus 1? Well, we know that if f sub n plus 1 equals f sub n minus 1 plus f sub n, we could move the f sub n to the other side and solve for what the smallest of the three terms is in terms of the other one. Correct? If the largest, if fib of n is defined in terms of the two smallest ones, we can define the smaller one in terms of the two larger ones. So let's now do that. That now gives us, okay, f sub n plus 1 minus f sub n. Correct? This is now f sub n plus 1 squared. This is now f sub n. Let's think about this. We've now got f sub n times f sub n plus 1, f sub n times f sub n. We could now factor out the f sub n, right? There's an f sub n times this and an f sub n times that. This is going to be a negative term. That's going to be a negative term. Okay? This, I claim, can be written as f sub n plus 1, f sub n times f sub n plus 1, f sub n. Okay? Any questions? If so, now that you've got these two, f sub n plus 1 and f sub n, that can now be written as f sub n plus 2. Okay? This tells us that this sum is now minus f sub n times f sub n plus 2 plus f sub n plus 1 squared. This looks just like the previous thing, except the indices have been increased, which is what we want in a inductive kind of argument, and the sign's funny. Well, if we multiply both sides by minus 1, the negative sign goes where it belongs. It clears the negative sign from here, and it increases the exponent on the negative 1. Any questions about that? Okay. Again, the Fibonacci numbers are fairly easy to work with, and you realize that the basic tool you have is induction and substituting that easy recurrence back into it. Any questions? Okay. Now, Cassini's identity is an interesting thing, okay, for several reasons. Okay, any questions about it? Look at this identity for a second, okay, and let's then see if we can figure out something about it. So let's see what it's actually saying. F sub n plus 1 times f sub n minus 1, okay, minus f of n squared is minus 1 to the n. Okay, look at that. Now let me show you a magic trick. Okay. Suppose I take an 8 by 8 grid of squares, and I cut it into pieces like this. Okay. Here I've got a this piece is a triangle. It's 3 by 8. This one's another triangle. It's 3 by 8. These two are also symmetric if you take a look at them. Okay, they go, one that's basically going to 3 by, it's a rhombus 3 by 5. The other one's 5 by 3. I claim that I can carve up the 8 squares, okay, the 8 by 8 squares into these 4 pieces. Does everybody agree? Okay. I now take a look over here. I can now rearrange those pieces. Okay. Here we've got our 3 by 8 piece. Here we've got our 3 by 8 piece. Here we've got our 5 by 3 piece. Rhombus is here. I can take these pieces and rearrange them. Okay. Does everybody see that? What's the magic involved with this? Doesn't look like any magic. Nothing mysterious. Except, how many squares are there in each one of these things? This is 8 by 8. Okay, right? How much is this? This is 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. How much is 5 times 13? 65. How much is this? 8 by 8. So how did I rearrange things to get an extra square? Okay. If I could do this by cutting it and rearranging it, this would be a great way to make material, right? Okay. So what's going on here? Okay. Does anybody see where there might be some connection to Cassini's identity here? Okay. What was Cassini's identity? Okay. Cassini's identity said to us that f sub n plus 1 times f sub n minus 1 minus f sub n squared was equal to minus 1 to the n. Okay? Does anybody see where there's any connection here? Okay? What's the connection? Okay?
If we take f of n plus 1 is 13, f of n minus 1 is 5.
So if we count the Fibonacci numbers, this is 8 times 8. Okay? The Fibonacci number above 8 is 13. The Fibonacci number below 8 is 5. So lo and behold, this says, if you look at it, that in fact the difference between the Fibonacci number squared, okay, the square of a Fibonacci number and the product of its previous and smaller one is very, very small, right? It's a difference of only 1. Okay? So what's the secret behind this trick? The truth is that, in fact, in this particular layout, we have got the product of two rectangles that are almost exactly the same size. They're so close to each other, they only differ by 1. That 1 is hidden by this line being too thick. That's really what's going on. If you look at, I once drew some pictures more carefully. Here is the original dissection. If you very, very carefully put those pieces together, okay, in fact, the missing square, the extra square, is really this tiny, tiny hole between them that doesn't show up on printing. Okay? Any questions about that? Okay? Something to go away and think about and maybe amuse your friend. You can amuse your friends perhaps with this. Okay? Where did the extra square go? Any questions? Okay? But yeah, they went through Cassini's identity. Any questions? Okay? So the Fibonacci numbers are fun to work with. Okay? There's lots of identities associated with them. Okay? And they come up surprisingly often when you want to count things. Okay? That's one of the things that makes them satisfying. And the reason they come up often is because the recurrence relation that defines them is so simple. As I remember last year, when I was teaching my CSE, my undergraduate discrete math class, 113, there was a question about how many ways there are to climb a set of n stairs when you're allowed to climb either one step or 2 steps. Okay, so I don't know if you when here I have a set of stairs. Okay, I can go 1 step at a time, or I'm big enough to go 2 steps at a time. But if I go 3 steps, I would hurt myself. Okay, how many different ways are there? Let's take a look at this. How many different ways are there if I have a staircase of n stairs? Let me try to do this online. If I ask you how many ways are there to climb n stairs where you're allowed to make 1 step or 2 steps, okay, how many distinct stair traversals are there? Okay, let's maybe try a smaller staircase. Here's, let's say, 4 stairs. I could climb this by making a climb of 1, followed by a climb of 2, or I could make a climb of 1, followed by 1, followed by 1, or I could make a climb of 2 followed by 1, right? If I add an extra step, how many ways can I do it? Okay, again, if we want to go and enumerate it. After I make my first step, if my first step was 1, it would look like that, right? If my first step was 2, then now I'm at the situation where I've climbed 1, 2. I have only 2 steps left. What are my choices? I could climb 1, 1, or I could climb 2. I have 5 ways to climb those steps, right? How many ways are there to climb n steps if I'm allowed to climb 1 step or 2 steps at a time? Okay. Fibonacci numbers. Why the Fibonacci numbers? The number of ways to climb n steps is My first step, if it's 1, I now need to climb n minus 1 steps, right? And every possible way I could do that would be different. If I have 2 steps to set of steps to climb, if I take a big bound my first time, I have n minus 1 steps to be climbed, right? Lo and behold, it has to be the Fibonacci numbers, because this basic property still, it's basically the recurrence is there, okay? And this Fibonacci recurrence is lurking in lots of things, because it's just a very simple, basic recurrence. Any questions about how to climb stairs or anything like that? Okay, good. So the Fibonacci numbers come up a lot, and they are useful things. Since Fibonacci numbers are the simplest kind of recurrence relation, simplest interesting recurrence relation, okay, we can use this as an example of how to solve recurrence relations, okay? We talked a little bit about generating functions before. I'd like to now try to show you an example of how you solve a recurrence relation using generating functions. Okay, we're going to go through generating functions in more detail in the next couple of weeks. Okay, but I think you'll be able to see sort of the ideas of how recurrence relations can be solved using them now. Okay, and we'll go through more of the mechanics a little bit later. By finding a closed form, what we would like to do is to find if we know that f sub n is equal to f sub n minus 1 plus f sub n minus 2. But if I ask you to use this recurrence relation and to find the millionth Fibonacci number, you've got to do a million additions, right? By finding a closed form, by solving this recurrence relation, we'd like to find a formula that one can plug in on a calculator to tell you what the nth Fibonacci number is without actually iterating through the recurrence. That's what it means to solve a recurrence. Well, let's look at how we can use generating functions to do so. What were generating functions? Well, they were ways of representing a sequence of numbers, right? That's all that a generating function was. Okay? And we could think of the generating function for the Fibonacci numbers as the 0th Fibonacci number times z to the 1 plus the 0th Fibonacci, the first Fibonacci number times z to the 1 plus the second Fibonacci number times z squared, ... My claim is that if we do this, we now have an alternate representation of the Fibonacci numbers. Okay? But there's nothing mysterious we have done now. We have simply, instead of writing the Fibonacci numbers, listing them in order, we listed each number, paired it up with it, sort of z to the nth Fibonacci number was z to the n. Any questions about this? It's just writing it down. But what power does it give us if we've written that thing down? Okay? If you remember last time, okay, well, we showed that by multiplying a generating function by a value of z, it had the effect of shifting the sequence over one spot. Remember that? Okay? And if we divided it by z, it shifted it over the other way. We also know that, by definition, if we know that f sub n times z sub n, we know f sub n, if that's the nth Fibonacci number, we know that f sub n times z sub n is going to be equal to f sub n minus 1 times z to the n plus f sub n minus 2 times z to the n. Why? Well, it's just a question of factoring it out. I mean, that's not an interesting thing. If you're telling me that I've got f sub n, z to the n, and you're telling me that f sub n is equal to f sub n minus 1 plus f sub n minus 2, then by definition, this is going to be equal to z to the n times f sub n minus 1 plus f sub n minus 2. Correct? Nothing mysterious at all here, right? So I claim I can write this as the sum. I could also factor it out a little bit. So I get something that looks like this. Plus I could factor z to the n times f of n to minus 2. I could factor out a z squared. Correct? By just rearranging the terms and pulling out a power of z here and 2 powers of z here. This has to equal that. Correct? Shouldn't be anything. How many people see this? It shouldn't be anything. It's just algebra. If you don't see it, raise your hand, because I'm happy to explain it. Okay? So what do we know? My claim is we know that f sub n is times z of n is going to be equal to these two things. Okay? Therefore, let's look at what that means. Okay? If we did this for all terms, this says that any one term of this generating function, okay, can be expanded into two terms, okay, with different coefficients. Suppose I now sum up. Okay, let's consider the generating function f sub z, which is going to be the sum of all of these terms. Certainly we know that f sub z is going to be equal to this, right? My claim is z times f of z. What is z times f of z going to be? Okay, if you want to think of it that way, okay, it's going to be equal to shifting the sequence over by 1, right? So z times that is going to give me f0 times z, f1 times z squared, f2 times z cubed, dot, dot, dot. Correct? And similarly, okay, z squared times f sub z is shifting it over 2 places, right? What if I now ask you, what is f sub z minus z f sub z minus z squared f of z? All the terms are going to cancel except for what? Okay, why is it going to cancel? Because we know that here we've got f sub 2 z squared minus f sub 1 z squared minus f of 0 z squared. What is f of 1 z squared plus f of 2 z squared? Plus f of 1 z squared plus f of 0 z squared plus f of 1 z squared. What's that equal to? f2 z squared. If I'm subtracting both of these all cancel, correct? So what I claim actually is, I've just shown, that the generating function f of z times, if I factor out f of z from here, I get 1 minus z squared, right? This thing has to be equal to z, because the only things that don't cancel are this and this. F of 0 is 0, so that didn't cancel but never existed. This 0 is going to go away. F of 1 is 1. I claim that what we're left with is this. Any questions? Okay. What's interesting about that? Okay. What's interesting about that is we have just shown that f sub z, okay, the generating function for the Fibonacci numbers is equal to z over 1 plus z minus z squared. Okay? Any questions? Okay, that you should believe I just showed you. What you can do with it is not clear. Okay? But it should be clear that I've just shown you that the nth Fibonacci, that the sequence generating function for all the Fibonacci numbers is this thing, right? What do I now want to do? If I could take this thing and find a way to describe the Fibonacci number, the sequence that it's generating, okay, in a different way, then that would be giving me what the Fibonacci numbers are, correct? Okay? Let's now think what this thing is, okay? Any questions? Okay. The first thing I'd like to tell you is, if we know that the nth Fibonacci number, all the Fibonacci, the generating function for the Fibonacci numbers looks like this, let's look at what this thing really means. Okay? I claim we can find a way to break this thing down, okay, into Fibonacci, into generating functions that we sort of know how to solve. If you remember last time, I showed you that the generating function for 1 over 1 minus z, based on the infinite geometric series, was 1 plus z squared dot dot dot. Correct? Does this look familiar or believable? Okay. If I know that the nth Fibonacci number is, that the generating function for the Fibonacci numbers looks like this, and I know that if I could expand this thing, it looks like that. If I could show you how to break down this function into terms that look like this, I claim I'm getting another way to think about the Fibonacci, about what this sequence is. Correct? What if I could write, okay, my sequence z over 1 minus z squared as a over 1 minus alpha z plus b over 1 minus beta z, okay, where these are constants and these are constants. Okay? First of all, is it clear that I can do that? Okay? Let's just look at this as algebra. Okay? Suppose I want to find constants a and b, alpha and beta, such that this equals that. Is that a kind of thing that you could figure out how to do? Okay? I think you could. Okay? Why? Well, first of all, if you want to think of it, what does this mean? Okay? If we add these two fractions together, what that really means is that that this thing is going to be equal to a times 1 minus bz plus b times 1 minus alpha z, right? So if they're going to be equal, okay, my claim would be that in fact, therefore, you're saying that z equals 1 minus z squared, that this is going to have, the denominator is going to equal the denominator of the combined thing, and the numerator equals the numerator of the divine thing. Okay? Correct? So you should be able to find those constants. Okay? In fact, that's sort of just solving, if you want to think of it this way. This is just solving a quadratic equation to figure out what those constants are. Right? We know that if for the case of the denominator, if we want that 1 minus z squared is equal to this, we can multiply this thing out. We're going to have here a 1 term, a z term, and a z squared term. Here we're going to have a 1 term, a z squared term, which is alpha beta z squared, and we're going to have a z term, which is minus alpha plus minus beta. Correct? So if you do that, we learn that alpha times beta has to equal minus 1, and alpha plus beta equals 1. Okay, correct? So we know that by plugging in beta minus 1, beta is equal to alpha minus 1 into there, we know alpha equals 1 minus alpha times minus 1. This is something you solve by the quadratic equation. Remember the quadratic formula from high school? Okay? You could solve this in high school. It means you could probably solve it now if you had to. What was the quadratic formula? It said that the root of a quadratic equation, okay, was, you know, it was, what was it? It was minus b plus or minus the square root of b squared minus 4ac over 2a. Does that sound right? Okay, so you could solve for that, right? My claim is if you solve for that, you can get what those constants alpha and beta have to be, right? And if you do that, we now know that this thing could be equal to that instead of alpha and beta. Once you fix alpha and beta, okay, you now can solve for what A and B have to be. Because if you look at it here, there's a, if you multiply this thing out, there's a 1's term and a z term when you multiply those out. The 1's terms have to be 0. The z terms have to be 1. You can find out what those coefficients are. Okay? So what have we just done? This may be for any questions so far. Okay? Before you get lost in a sea of algebra, see what we've done. Here was the Fibonacci number, generating function, right? I claim that I could write this thing as this plus this for constants there and constants there. Correct? Do you believe that? Okay. What good is that? Well, I know that if I have something of the form 1 over 1 minus alpha z, this thing can be, that part can be expanded by, okay, becomes 1 plus alpha z plus alpha squared z squared dot dot dot. What is big A times this thing? Okay? That's going to multiply each one of these terms by big A, right? And now I've got a sequence of an infinite number of terms, right? What is this thing going to be? Okay? This thing can also be written as a natural sequence of, sort of b times beta to the n times z to the n, right? And the total sum of this thing has to be equal to this plus that. Okay? Any questions? What it means is, once you work through the math, okay, we've shown that this thing, this big complicated thing, can be written as A times B, basically being, this was A over 1 minus alpha z. We solved, used the quadratic formula to find alpha. We used the quadratic formula to find beta. We can solve for what those constants are, A and B. Those happen to be that. Okay? Now what are we saying? Each one of these sequences can now be expanded. Okay? And that we can now rewrite one of this thing as, if you want to think of what are we rewriting that thing as, we're writing it as, the first is A times, okay, if we want to call this thing alpha, this was going to be alpha to the 0 times z to the 0 plus alpha to the 1 plus z to the 1 plus alpha squared z squared, right? That was what we were doing. Okay, that's what it meant to blow these things up. Okay? The sum of, so that's what this sequence is going to be. The second sequence will be written as, okay, something similar. 0, z, 0, plus beta to the 1, z to the 1, plus beta squared, z squared. So what do we know that this, if this is true, what do we know that the value of the second Fibonacci number would be? It's got to be alpha A times alpha squared plus b times beta squared, right? Because we said that this is the generating function for the Fibonacci numbers. We are finding a way to write it out as expanding it in terms of powers of z, okay, collecting those terms together, collecting both the terms that correspond to z sub n is going to be what tells us what the coefficient of the z sub nth term is going to be the nth Fibonacci number. What that coefficient is simply the sum of two of these things. Okay? Namely, it's going to look something like, for a given value of n, it's got to look something like this. We found what those constants were. I claim that, therefore, the value of the nth Fibonacci number, when you plug in the constants, has to look something like this. And in fact, this is what it is. This seemingly gruesome-looking function that you wouldn't have seen otherwise, okay? I mean, it's not obvious when you look at this, the Fibonacci numbers at square root of 5s lurk any place, okay? But it falls out of a direct consequence of our generating function analysis. Any questions? How many people have a vague idea of where we got this thing from? Okay, how many people feel lost? Hopelessly lost by this? A few people, okay? Let's go through this just a little bit more, okay? Look at some consequences of it. If this is the solution, okay, which in fact it actually is, let's look a little bit at what this tells us about the Fibonacci numbers, first of all. What's the impact of the solution? Okay? This is going to be 1 plus the square root of 5. What's the square root of 5? Okay? It's 2 plus something, right? What's 2 plus something over 2? Okay? 1 plus something, right? Okay, that's good. What is 1 minus the square root of 5? What is 1 minus 2 something? Okay? Actually, what? Okay. That's minus 1. Minus 1, right, it's going to be minus 1 something over 2. This, I claim, is going to be something that's less than 1, correct? 1 minus 2 something divided by 2 is less than 1, right? So for large values of n, what happens when we look at this thing? Okay, how fast does the Fibonacci numbers grow? Does this thing ever contribute a lot to the final term? No, 1/2 to the n is 1/2. The more you raise it to an n, the smaller it gets, right? So this isn't really that important. It's important to make it an integer. But in fact, this doesn't do much for you. The big real value of the Fibonacci number is 1 plus 5, square root of 5 over 2 to the n. That's really the rate of growth of the things, okay? And in this particular number, 1 plus the square root of 5 over 2, is a number that comes up a lot. Does anyone know what that number is? Golden ratio, right? So, in fact, what this is really saying is the Fibonacci numbers grow as the golden ratio to the n, correct? Okay? So another reason why Fibonacci numbers come up a lot is because the golden ratio comes up a lot, or vice versa. Okay? When people brag about the golden ratio coming up in architecture in the shape of human body proportions and whatnot, they're really seeing the Fibonacci numbers somewhere lurking in there. Okay? If they're seeing it anywhere. Any questions? Okay? Okay. Any other questions? Let me just show you one thing that I think is the single most confusing thing about this whole solution to the Fibonacci number. Okay? I think if you go back and look at this in a rational way, you will be able to believe, based on this thing, that in fact f sub z is equal to z over this. This is something easy to see if you look at algebra. I have no problem seeing that. Okay? You will have no problem seeing, okay, if you're fair-minded and willing to do the algebra, you should have no problem seeing that you can write this funny thing, expand it out so that you factor it out into two of those terms, right? That's something you should be able to do. That's algebra. What is the fishy-looking thing? The thing to me that's fishy looking is always this. How do you go from one of these fractions to an infinite sequence of things, right? Looks kind of funny to me. Maybe this will convince you of this. How many people does that look funny to? Just like a lot of people looks funny to. Okay? Where does it come from? Maybe this will make you feel better. Okay? Well, what is, I claim that 1 over 1 minus alpha z is equal to this power series. Why is that? Well, look at the following. What is that power series times 1 minus az? If this identity holds true, what is that power series times 1 minus az? What should it be? 1, right? If I multiply both sides by 1 minus az, I got to get a 1, right? Well, what happens if I do multiply both sides by 1 minus az? This is going to be 1 times 1 minus az. This is going to be az times 1 minus az, and so you do and get az squared, a squared, z squared, right? You get a squared. What do you see? You see a telescoping sum, don't you? This term is minus, this term is plus. This term is minus, this term is plus. By the time they finish vaporizing each other, what's left? Only 1. Okay? So maybe if you look at it this way, why is this thing equal to that? Well, it's certainly equal to that if you multiply it both sides by that. Okay? Is this convincing? How many people now find this convincing, that this equals that? Okay? Again, it still looks mysterious, but it should be convincing. And if you believe that, then we've sort of got basically all the machinery that we need to start to solve recurrences using generating functions. We'll see more of that later on. But you should have now seen the basic strategy. You find a closed form for your generating function. Okay? So this is the Fibonacci generating function written in small print. The small print thing, you expand, okay, until it is of the form of some kind of generating functions you know how to expand. Okay? And 1 minus 1 over z is a good example of something you know how to expand. Once you now know how to expand them, write out what those terms actually are and do the arithmetic yourself. And that's really where we came out with the solution. Any questions about that? Okay, any questions about anything with Fibonacci numbers? Okay? So think about that. We'll be moving into generating functions more seriously. But think about that. Go back over that to convince yourself of the general strategy. Any other questions? If not, thanks for your attention. See you next time.